Dear Professor Yang, Professor Mai, colleagues, students, ladies and gentlemen, good morning. My name is Qing Yan Chen. I'm the director of the PolyU Academy for Interdisciplinary Research. I'd like to welcome all of you to this distinguished pair lecture. So today, I have a great pleasure to introduce our speaker, Professor Robert Yang, who is an emeritus professor of polymer science and technology at the University of Manchester. Professor Yang is internationally renowned for his pioneering work in polymer science, composite materials, and advanced nanomaterials. His research has greatly deepened our understanding of how material structure governs the mechanical behavior, spanning high-performance fibers and carbon fiber composite to cutting-edge materials such as carbon nanotubes and graphene. So a hallmark of Professor Yang's work is his innovative use of Raman spectroscopy to monitor the deformation of fiber and composite. This breakthrough approach allows researchers to observe mechanical behaviors at the molecular level. This is an amazing achievement. So his research has also led to some truly creative applications. For example, his team developed the highly stretchable and sensitive sensors using graphene mixed with a common children polysilicon toy, silly putty. Well, I don't know this is that, but it looks interesting. Yes, demonstrating the exciting potentials for medical diagnosis. In another application, his work helped create the world's lightest mechanical chronographic watch with a graphene-enhanced composite case weighing just 40 grams, including the strap. So Professor Yang's achievement has been widely recognized. He is a fellow of the Royal Society and the Royal Academy of Engineering, and we're also very proud he's also a senior fellow of PAIR. So without further ado, ladies and gentlemen, please join me in welcoming Professor Yang.
Yes, thank you, Professor Chen, for that very kind introduction. It's always nice to come to PolyU. I've been here many times and had many links with it, and now I'm happily one of your pair fellows. Today, I want to give a general summary about our work on the mechanics of graphene and graphene-based nanocomposites. It's about just over 20 years since graphene was first identified and isolated, and there's been a lot of interest in the material, and in Manchester, the work took place that identified it, and we've been collaborating for over that time with our friends in physics, and now I think we're starting to understand how this material works and how we can use it. Of course, the work has all been done by my collaborators, several Chinese students and postdocs of mine, also Ian Kinloch and Dimitrios, and Novoselov, Kostya Novoselov, who of course was one of the Nobel Prize winners. He started work in this area. So there's a lot of people to thank, and all the work has really been done by other people. I'm going to concentrate particularly on graphene itself, and then also graphene nanocomposites, just to see how these things all go together. Right. Carbon. When I was a student, we had two forms of carbon. We had diamond and we had graphite. And it was a boring material, and nobody was particularly interested in it. And in the last 30 years, there's been revolutionary things happening with carbon-60, carbon nanotubes, and also, of course, graphene. And the very simple experiment that was done by my colleagues in Manchester 20 years ago was to take some graphite and to use some adhesive tape peel off layers and then press a layer onto a substrate and pull it off, and you end up with a single layer of the graphite lattice. So this graphite can be split into individual single atomic layers. And this work really revolutionized an area, and the whole area just exploded enormously because this material has some really quite interesting properties. These were some of the properties that people started to identify early on with graphene. It was the thinnest material you could possibly have. It's only 1 atom thick, third of a nanometer thick. So that's the highest specific surface area of any material. It's almost transparent to light. It absorbs a little bit of light, but it's nearly transparent to light. Of particular interest to me is the stiffness. It has a mechanical stiffness of 1 terapascal, 1,000 gigapascals, 4 times stiffer than steel. And we have strength estimated at 130 gigapascals, which is the most enormous level of strength. And that's something I want to talk about a little bit. But there's also other properties: record high thermal conductivity, very high electromobility, carriers going around relativistically. A lot of physics can be done. And chemically, you can do things with it as well. You can also use it as barrier materials or filters. There's lots of interest in that sort of area. So the whole area just exploded after the first paper in Science in 2004. And it led in 6 years to the award of the 2010 Nobel Prize for 2 of my colleagues, Professor Novoselav and Professor Guy. So this was a really very exciting piece of science. At the time, I was head of department and I couldn't get going on the material quick enough, but eventually we started to work on it as well. So we have the Nobel Prize. Now, of course, the British government were very pleased that we won a Nobel Prize, and so they decided to award an institute to the University of Manchester. Some $80 million was found, and they also got some European money. We were a part of the EU at the time, so the European Union put some money in. And we had this institute after the Nobel Prize, and eventually it was opened in 2015. So it was opened about 10 years ago. And I have an office in this institute, and there's 200 researchers from different different departments in the university, different schools, and it's a big interdisciplinary activity. The government was very proud of this, and so in 2015, later in the year in 2015, we had a visit from President Xi of China, and so President Xi was brought to see our institute. In fact, my PhD student acted as his interpreter, which is quite interesting. So politically, the whole thing just sort of exploded, and you can see what the sort of things happening. We also had royal people coming. We had the Prince of Wales and Princess came. They wanted to see the institute, so everybody was sort of coming to see the institute. It was really, really a very exciting time. Yeah, the Prince of Wales heard about a graphene enhanced car here, and he wanted to try it. So yeah. So anyway, that's the sort of politics of the situation, but let's perhaps get onto some science. So what happens in the National Graphene Institute? Well, we have different groups in the institute. I'm involved with the materials activities, but we have fundamental physics. We have 2,000 square meters of clean room. We have a doctoral training center. We have activity in life sciences, chemistry of composites, and also electronics of composites and sensors. There's about 30 different academic groups in the Graphene Institute working in all these sort of areas. And this is a cross-departmental activity, a physical activity, which seems to work well. Now, let's get down to the science. I want to talk about the mechanics of graphene and the mechanics of graphene composites. The first question is, although we've seen the headline figures, does graphene really have good mechanical properties? And can you use these properties in nanocomposites. And what tools do we need to look at the properties of the material? And the sort of properties we're looking at are the stiffness, the Young's modulus, the fracture energy, and the fracture strength, the fundamental properties. This material here, which is just one atom thick, what are its properties? How can you actually test it, something one atom thick? It turns out it's really fairly straightforward to test. Now, one particular property that's come out of our findings is the aspect ratio of the material, essentially its length divided by its thickness. Its shape mechanically seems to be, as we'll see at the end, just as important as its fundamental physical properties. So, and of course, there's a lot of interest around in 2D materials, all types of 2D materials. And so I think we've got some general rules that come out for all 2D materials as well. So let's look at the first mechanical property measurement done. This was a paper in Science in 2008 by Jim Hone in the States. And they took a monolayer of graphene across a silicon wafer with holes in it. And they used a cantilever to indent the graphene, and they pushed it until it broke. And they measured the force and the displacement, and they generated a stress strain curve, standard stress strain curve, stress against strain. And you can see here that they have a very high slope of the stress strain curve. This is the measured one. There's also a calculated one in another paper. And the initial slope of that gives a modulus of 1,050 gigapascals. That is 4 times steel. No, 5 times steel. And that also, they measured this most enormous strength of 130 gigapascals. Absolutely enormous strength. And so the question is, are these two measurements realistic, or can we use them in other applications? And the interesting thing about this experiment is that the deformation is concentrated in a very small region of material, just under that tip. It works out about 10 to the 4 atoms. So here we are sort of doing mechanics on the atomic level. And I think the mechanics on the atomic level is quite different from that on the sort of bulk level, as we'll see. But anyway, this was the experiment, and it led to this sort of headlines such as, it's as stiff as diamond, 200 times stronger than steel. Well, a lot of people have used that, those sort of claims, and I think it's certainly as stiff as diamond, but certainly not 200 times stronger than steel, as we'll see. So let's look at how you would measure, follow the deformation of this material. And it's perhaps rather strange, but we had a lot of experience, as we heard in the introduction, about using Raman spectroscopy for looking at the deformation of materials, particularly carbon-based materials. Now, Raman spectroscopy is a very interesting technique where you take a material, you shine a laser beam on it, you look at the scattered light, you analyze the scattered light, and you get a Raman spectrum. You can essentially do it under a microscope. So you have a microscope here with a spectrometer on the side of it. You have a laser spot about 1 micron in size, focused on the material, and you can get spectra for most 2D materials, and you can characterize enormous aspects of these 2D materials just from their Raman spectrum. Raman spectroscopy was developed by an Indian scientist. He got the 1930 Nobel Prize for this technique. It was almost forgotten until the 1960s and 70s when lasers came along, and lasers absolutely revolutionized Raman spectroscopy because you need monochromatic light. You need a strong monochromatic light beam. So once lasers came along, the whole technique exploded and is used for a lot of applications now. But it's particularly good for carbon-based materials. You can use it for many other things. So this is the Raman spectra of graphene. So this is an optical micrograph of a specimen, one of our first specimens prepared for us by Professor Novoselov. So we actually had a Nobel Prize winner making specimens for us. And he produced us this specimen, which had a monolayer. This ghostly outline here was a monolayer, just looked at in the optical microscope. It's sitting on a substrate, a glass slide, I think this particular one, on a glass slide, just a monolayer there. You can see the size of it. It's 10 microns or so across. And there's some bilayers and trilayers and other sort of material here. Now, the nice thing about Raman spectroscopy is you can look at the Raman spectrum and you can see this is the Raman spectrum, which is the intensity of the scattering against the wave number, essentially the frequency of the light. And you can see that monolayer has a different spectrum than bilayer, has a different spectrum from trilayer, a different spectrum from 5 layers. So you can just put your specimen into the Raman spectrometer and you can see if it's monolayer, bilayer, trilayer, or whatever. We can actually just count the number of layers. So that's sort of quite useful in characterization terms. And the spectrum, even though this is only 1 atom thick, so it's a 1 micron spot on a 1 atom thick material, you get a strong spectrum because of the electronic structure of graphene is such that you get very strong resonance Raman scattering. So it's sort of a material made for Raman spectroscopy, graphene is. It's just the perfect material. So that was the first thing that we'd done. And we'd done this sort of work on carbon fibers before for many years. And we knew that for carbon fibers, these bands in the Raman spectrum, these peaks in the Raman spectrum were sensitive to stress. And we were interested in what was the case, what was the situation in the case of graphene. So this is some of our really old work on different sorts of carbon fibers. These are pan-based carbon fibers, standard carbon fibers, the sort of carbon fibers you see in modern aircraft. And they have these 3 bands in them. Yeah, you see there's actually a 3rd band here, which is usually quite weak in graphene, but there are these 3 main bands. You see the same bands in the carbon fibers. This is pan-based carbon fibers, and this is pitch-based carbon fibers. And you have the bands are called D, G, G for graphite, D for defects, G for graphites, and 2D for overtones. And you have all these bands in carbon fibers. And what we discovered in the 1980s was if you stretch a carbon fiber and you look at the individual bands, the bands actually move under stress. So this is black is the undeformed fiber, and blue is the fiber with just a small strain on it. And you get this massive shift in the peak position of the Raman band. And if you plot the peak position against strain, then you get pretty well linear behavior. And what we found was that the slope of this line tended to increase with increasing fiber modulus. The stiffer the fiber got, the higher the slope of the line. So the line just becomes a higher slope. And these are 3 different carbon fibers of different stiffness. Here's our technique. We just take a single fiber, we stretch it, when we shine the laser on it and just look at this peak shift. Very simple experiment. It takes about 10 seconds to obtain this peak. It's a very quick technique just to obtain the spectrum in the modern spectrometer. And what we found was that if we plot the slope of these lines, which is peak position against strain, if we plot the slope of those lines against the tensile modulus of the fiber, so this is now the shift rate, the slope of the line, against the fiber modulus, that you get a sort of roughly linear relationship. Low modulus fibers are down here, high modulus fibers up there. This is our highest modulus fiber with 800 gigapascals, P120 pitch-based fiber, had a shift of over 40. So we found that the shift rate is proportional to the stiffness of the fiber. So it is also universal calibration for all forms of graphitic carbon, presumably also for graphene. So when we did this experiment on graphene, we found similar things. So we now took our single layer, monolayer graphene, put it onto a plastic beam. We then deform the beam, which then deformed the graphene, and we looked at the behavior, and this shows you the setup. You can see this is the Raman spectrum of pure polymer. This is the Raman spectrum of polymer with graphene on it. And you can see the graphene, although it's only 1 atom thick, we can see the spectrum from it, although the PMMA was 3 millimeters thick. So it's a very strong effect. And if you look at this particular peak, undeformed, it's here, 1.3% strain, it's there, 1.8% strain, it's there. Massive shift of the band. And if you plot the peak position of that band against strain, you get a slope of about -55. And we go back to our previous plot here, our carbon fiber calibration. A slope of -55 is off the top here. It's about up here. And it corresponds to a modulus of about 1,000 gigapascals. So it means that the modulus of this material is 1,000 gigapascals. So that's what people found mechanically. That's what we found with Raman. So that's the first thing we've got. Now we want to see the behavior in a composite. So we then decided to make a model composite, again with Professor Novoselov. He produced a composite like this, where we had a polymer beam with a graphene monolayer, 1 atom thick, sitting there, sandwiched between 2 polymers. We then deformed it, and then did measurements along the length of the graphene. And we measured the strain in the graphene using our calibration in the previous slide against position. And we found our data points are there. And we found we got this sort of behavior on this curve. And people who know about composite mechanics would immediately say, well, that looks like what you get if you put a fiber in a composite. And you can use this theory called shear lag theory, which tells you how the stress varies with length along an embedded fiber. And it's pretty well the same mechanics from an embedded graphene flake. And the solid line here is the theoretical line. So it tells us immediately that although this material is 1 atom thick, that shear lag theory and continuum mechanics seems to work really well. And that is something we'll use later on in our analysis. Now, what I want to do is to look at the strength now. We heard of this massive strength, 130 gigapascals. Is that really the case? So we decided to try and break some flakes. So here's a flake, monolayer flake. This is probably about 50 microns long. We stretched it in the vertical direction. And then we mapped the Raman spectra over 1,000 points on the flake. So a student spent his whole Christmas measuring flakes, thousands of measurements all over these flakes to map out the strain in the flake as you deformed it. So we start off in the undeformed state, 0% strain. And you can see here, this is our sort of rainbow chart here of strain. You can see that it's fairly undeformed. Then we go to 0.7% strain. We start getting hot spots in the material. And then at 0.9% strain, we get hot spots and a blue area here where we've had a crack. So we've actually broken the flake. We've actually done a fracture experiment on a single layer of atoms. We've looked at the strain needed to break a single layer of atoms. We tried it on smaller flake. This was a smaller flake, only about 10 or 20 microns wide. This one, we couldn't break it. This one slipped. The interface failed before it would break. This one here is a fairly narrow one. Again, we couldn't break it. It just got a high strain in the middle. We just couldn't break it. So there seemed to be a size effect here. The big flake, we broke it easily. The smaller flakes, we couldn't break. And we looked at loads of flakes and found that these smaller straight flakes are stronger. And of course, that's something known that small things are generally stronger than big things because of defects. And we've done a lot of analysis on that. And what we've done here is there's some measurements here from lots of flakes we've looked at. Well, this is the stress required to break the flake. against the flake width. The large flakes, we can break them at about 5 to 10 gigapascals. The small flakes, we can't break them because in our setup, the interface fails. The flake just slides. So we have flake fracture for large flakes, and we have intact flakes for small ones. So we find typical strengths below about 10 gigapascals, but very narrow flakes, maybe really quite strong. And of course, the experiment that was done originally was under a point indenter where we had a very small area of deformation. So we have this interesting size effect and find that the large flakes are much weaker than reported. So that's the strength. Now we want to look at toughness, because as well as strength, toughness is important, and it's not the same as finger strength. Toughness is the propagating a crack, where strength is sort of initiating a crack. And we've been able to also to measure the toughness of graphene as well by looking at an existing crack in a flake. So we found this flake here, monolayer flake, rather fragmented, but it had an existing crack in it. It had a crack sitting down there. And from the polarization of the Raman spectrometer, we were able to work out the orientation of the graphene lattice, and we found that this was the orientation of the graphene lattice for this particular flake. We then deformed it, and we mapped out hundreds of data points around the crack and around the crack region. And this is before deformation, and this is after deformation. And you can see before deformation, there's a crack there. Then after deformation, the crack's grown, turned direction, and it was deformed in the vertical direction. So the crack has become 90 degrees to the stressing axis, which is what you might expect. But what we've done is been able to, this is the before and after experiment. I can show you what happened in the meantime. We got quite a lot of interesting information out of it. So this is now zoomed in to the data points around the original crack. Blue is undeformed, green is deformed. You can see a stress concentration at the tip of the crack. This is the orientation of the graphene lattice and the geometry of the setup. We then increase the strain, and the stress concentration builds up, and you can see a stress concentration sitting at the tip of the crack here. And then when we go to 0.41% strain, the crack grows, propagates, and changes direction, becomes perpendicular to the tensile axis. So we can actually do fraction mechanics on a monolayer of atoms, which is really quite exciting. So we also have these strain fields, and we know that stress is proportional to strain for this material. It's linear elastic. Therefore, we have stress fields, and we can work out the mechanics of what's going on. So there's just a little bit of mechanics here. We have to go to the textbook and find the stress field ahead of an inclined crack. We can go through the analysis of this. We can, ahead of the crack, we can look at the decay of stress, and we can then extrapolate back to the crack tip. We can work out the K factor. The K factor is a function of strain. And then we get to propagation at 0.41, which is the critical K, Kc. And we have 4 measurements here of the crack stress concentration increasing. And then suddenly the crack propagates, and we can work out the fracture toughness of 4 megapascals root meters, which is not a lot. So this is a massively strong material, which is not that tough. A fracture energy of 16 joules per square meter or so. But anyway, we can do this. And of course, in the literature, people have done this, have calculated this. And they've calculated it in this particular paper here, International Journal of Fracture in 2012. They calculated Kc for graphene to be between 3.7 and 4.2. And we measured 4.0. So we're pretty happy that we measured the actual value. And it's a pretty easy calculation to do because there's no plasticity in this material. This is a material which just goes elastically deforms and then breaks. There's no plasticity, no other deformation mechanisms can take place. And people have modeled that very nicely. And however, this toughness, I think, is about 10% that of steel. So it's 200 times stronger than steel, inverted commas, and only 1/10 as tough as steel. So, yeah, you have to be careful when you compare the material with steel. So that was monolayer graphene. What happens if you have few layer graphene? Because we know once we get to graphite, the properties don't get anywhere near as good. And this is because the layers slide over each other fairly easily. So we looked at this particular deformation of this particular flake, and this is quite an interesting flake because it had regions of black regions here of monolayer, then red regions here of bilayer, and then blue regions of trilayer. So we had monolayer, bilayer, and trilayer. And you can see from the Raman spectrum of the 2D band that you get quite different shape peaks. This is because of the electronic structure of the material is different with different number of layers down at this level. So that's quite interesting. But what we found was that when we looked in detail at these bands, funny things happened. When you deform the material and measured the peak position as a function of strain, for monolayer, we had a big band shift. Bilayer, we had the same band shift. Trilayer, we had a lower band shift. Many layer, we had a even lower band shift. And for graphite, we had no band shift at all. So what was happening? We had different slopes for different numbers of layers. Now, the monolayer shifted at, gave a modulus of 1015, but it's saying essentially that the modulus of the graphene is dropping as the number of layers increases. We have a lower modulus as you increase the number of layers. And that's a sort of funny effect, but probably makes sense because by the time you get to graphite, which has got loads of layers, the stiffness in this particular experiment is very low. And we can actually show that what's happening is that you're interested in what you need in this case is stress transfer between the different numbers of layers. What is this mechanism for the modulus reduction? Well, let's look in detail at the plots, and it's a little bit in detail, but quite interesting. I find that if you look at the band, this is the Raman band, on the same scale, 0.2.4%, you can see that this band is actually broadening as you deform it. So this is the peak position goes down, but the bandwidth actually goes up. The band broadens for monolayer. For bilayer, again, it's a different shape, but it gets broader as you increase the strain. The peak moves downwards and the width goes up. But trilayer is very odd. Trilayer, you find that you get a peak shift down of the peak position, the peak position, but when you look at the peak width, it actually narrows. So you've got the trilayer narrowing where the monolayer and bilayer broaden. So you've got changes in band shape with strain. Well, that may be rather subtle, but it's telling us that something's going on, which is quite interesting. And what's happening is the layers can't slide over each other very easily. And you get this band narrowing, which is rather odd. So we have different mechanisms here. And this is a sort of a schematic view of the different layers. So graphene has what's known as ABA Bernal stacking. You have A layers and B layers, and they are on top of each other. And I'll call the A layer black and the B layer red. And you can see that normally undeformed, they just sit on top of each other. But when you deform it, lots of things can happen. The layers can start to slide over each other, and you can get either affine deformation or non-affine deformation, or even the formation of partial dislocations and stacking faults, ABA, CBC, ABA, and partial dislocations. It turns out that this is, first of all, that's Bernal stacking retained. This is Bernal stacking lost, and this is Bernal stacking with stacking faults. It turns out this is a massively old problem. You can go back to the early days of electron microscopy in the 1960s, and people were interested in this particular phenomenon then. And And what it means is that for this 3-layer material, the A layers, the B layer in the middle doesn't follow the A layers. So you can see this is the polymer sandwich. You've got the graphene sitting there. And what happens is that the shear, there's a very low shear stress, very low shear, very low stacking fault energy. And it's very easy for the middle layer not to keep up with the outer layers. And so you get this situation of partial dislocations and these stacking faults. And we see it in the Raman spectrum. But you can go to 1964. This is a paper by Tony Kelly, who Professor Mai knew well, who went into composites eventually. But in his early days, he was working on graphite. And he was doing electron microscopy of graphite single crystals. And he was, would you believe it, preparing his specimens by repeated cleavage between sellotape, between adhesive tape. So he was doing tape exfoliation of graphite. And he was interested in these multi-layer materials where he could see basal dislocations and stacking faults in the material. So we've sort of gone full circle back to the original days. And in fact, was Tony Kelly the first person to isolate graphene? I asked him, and he said, any monolayer they threw away, it wasn't of interest to them because they couldn't do anything in the electron microscope with it in those days. So science is rather funny how things actually develop. Anyway, let's finally get on to nanocomposites. We've got this material, a nanomaterial, which has a modulus of 1,000 gigapascals. That ought to make a good nanocomposite. Does it? And we're interested in, can we realize these properties in nanocomposites? What analytical tools do we need to model the nanocomposites? And can we look at things like Young's modulus, fracture energy, fracture strength? And can we get really good properties in nanocomposites using things like graphene? And we'll see now what the situation is. And we've looked at graphene polymer nanocomposites. We've tended to use another technique for analyzing the material, which is X-ray computed nanotomography. This is where you have an X-ray source. It's like radiography, but you do it at the nanoscale, and you can do it in the synchrotron as well, as we'll see later. And I've got a whole facility with these machines, and it turns out it's very good at looking at graphene nanocomposites. This is graphene in natural rubber. These are graphene nanoplatelets, which are dispersed in natural rubber. And this is a scan through using our tomography. And you can see it's artificially colored of different orientations and different shapes. And it shows how you can actually see the individual flakes in the material. And it turns out, of course, that in a nanocomposite, the graphene is nowhere near as beautiful as you might expect. If you look at the individual flakes, this is again artificially colored flakes, you can see you get a whole family of different sorts of flakes in the material. You can get some flat flakes, you can get curved flakes, you can get partially fractured ones, you can get multi-layer ones, you get agglomerates. The whole thing can be something of a mess when you try and make a nanocomposite. If you just fragment some graphite and try and make a composite in this way. So you have to be very careful to know what you're looking at. You get big flakes, small flakes, whole range of different things. So let's look at some simple measurements we've done. We've looked at graphene and natural rubber. We've taken natural rubber, added some graphene to it, and then so we have a tensile test here, black specimen, stretches in the vertical direction, and what we've done here, we've got a series of stress strain curves of natural rubber, the black one here, and then natural rubber with different loadings of graphene nanoplatelets in the material. And you can see that as you add graphene nanoplatelets, the material becomes stiffer, which is what you might expect. You get that with carbon black, but it's better than carbon black. It does give quite a lot of stiffening, even at low loading. So that's quite interesting. We can try and analyze the behavior just using a simple rule of mixtures, which tells you essentially how the graphene is behaving. The rule of mixtures says the modulus of the composite should be the modulus of the filler times the volume fraction, the modulus of the matrix times its volume fraction. So if you plot the modulus of the material against the filler, volume fraction of filler, compare it, say, with carbon black, way down here, doesn't do a great deal, but with the M15 nanoplatelets we used, we get a slope, a straight line roughly. However, the slope of this line says that the graphene has a modulus of 40 megapascals. 40 megapascals. Okay, well, that's not very much. We know the graphene's got a modulus of 1,000 gigapascals, so 40 megapascals is not a great deal. Why is that? Well, I don't know. Let's look at another polymer. This is polypropylene. This is a stiffer polymer. We put graphene into it, get the stress strain curves. We work out the modulus here, and in this case, we get a slope of 15 gigapascals. So we're into the gigapascal region now, but still, this is using the rule of mixtures, still below the 1,000 that we expected. And we did this, we've done this for lots of materials. In fact, we analyzed data that people have got in the literature where we looked at the effective modulus of the graphene in this axis on a log-log plot against the modulus of the matrix. Because we found that the soft matrix materials, the graphene tended to have a low modulus. The harder materials, graphene tended to have a higher modulus. And we put our own data on this as our natural rubber. There's our polypropylene fitted in the literature data. And this had a slope of 1. This line had a slope of 1, which said that the stiffness of the graphene is proportional to the stiffness of the matrix. They didn't say, it wasn't 1,000 gigapascals, it just depended on the matrix, which is really odd. But when you go through the mechanics of everything, it actually fits in with shear lag theory and the stress transfer of stress to a reinforcement in a matrix. We've covered this in Progress in Material Science, a whole series of papers on this. But essentially, you can analyze it using shear lag theory. The problem is that if your matrix has too low a modulus, it's not able to transfer stress from the graphene. So you can't get good stress transfer with a low modulus matrix. You get much better stress transfer with a higher modulus matrix. And this is all comes out in the shear lag theory and essentially the stress in a flake as a function of its stress transfer coefficients and its geometry. It also depends on the aspect ratio of the fiber or the reinforcement is the most important thing, the aspect ratio, rather than its properties. So if you sort of look at our data now, sort of cleaned up here, this is where we do the log-log plot again of the modulus of the graphene against the modulus of the matrix, going from natural rubber, soft materials, more rigid materials, thermoplastic elastomers, epoxy resins. You find the graphene starts to get reasonable properties as you get stiffer and stiffer. And this particular line is asymptotic to 1,000 gigapascals. So because of the mechanics, because of stress transfer, you only get very high modulus values for the graphene for high modulus matrices. So that's a little disappointing, but in fact, it explains quite a lot. It also tells us that most 2D materials will work in a similar way. So you can look at reinforcement with graphene nanoplatelets. We can go through all the mechanics of everything. Another factor is orientation. We can factor in orientation. And for 2D materials, orientation doesn't have such a big effect as fiber orientation. So we can work out the effective modulus of the composite, and we can end up with a final equation for the modulus of the composite depends on the modulus of the matrix and the aspect ratio of the particles, but it's independent of the aspect rate of the modulus of the graphene. So the modulus of the graphene, the stiffness of the graphene, doesn't affect things. So it tells us that clay, all these other two materials, any 2D material would work as equally well as long as it's fairly stiff and it has a good aspect ratio and a good orientation. its actual properties are not that important. So that's quite interesting finding. And you can see aspect ratio is important here. This is an experiment we did where we plotted the modulus of the composite divided by the modulus of the matrix against the volume fraction for different aspect ratios. And you can see here the higher aspect ratio particles gives better stiffening than the low aspect ratio particles. And you can measure the aspect ratio from the CT scans. So let's look now at fracture of these materials. And I want to just go through failure of the materials. And that turns out to be quite interesting and also related back to conventional composite mechanics. If you look at a fracture surface here of a torn graphene reinforced rubber, you see all these pulled out flakes. You can see the pulled out flakes. And clearly, what happens is that when the material breaks, what the flakes do is they just debond and pull out. They're too strong to break. They don't break, they just pull out. So all the energy, all the toughening in this case is not due to the strength of the graphene, it's just due to mechanisms such as pull out and debonding. And you can go through the maths of it. The energy for debonding is given by this equation. Again, depends on the aspect ratio. And the fracture energy for sliding and pull out is again by this equation, again, depending on the aspect ratio. Aspect ratio appears all the time in these analyses. So what you'd predict was the fracture energy is proportional to the volume fraction, and fracture energy is proportional to aspect ratio. So if you look at fracture of various nanocomposites, this one is epoxy toughened with GMPs, proportional to the volume fraction, the energy, the excess energy, tearing energy of a rubber, proportional to volume fraction, tearing energy proportional to aspect ratio. So it all sort of works out quite nicely on standard conventional theory. However, it's independent of the filler strength. So again, the strength doesn't matter. It's 100 times stronger than steel or whatever, but doesn't matter. You never achieve that. You never see that. You don't need it. However, when you go through the details of these analyses, you find that you get very high levels of fracture energy, tear strength. And this is an example for an FKM rubber here. We did a tear test for this material. This is our sort of standard tear specimen. It's a rather odd ASTM specimen, but essentially you can measure the tear strength against the loading, much better than carbon black, as you might expect. And you get the slope here, which predicts a very high tearing energy, much higher than you'd expect for debonding and pullout. Something else must be going on. And this is the something else that's going on. If you look at the opposite fracture surfaces of one of these torn specimens, you can see that you get holes on one side, and there's the hole, and there's the pulled out flake. There's a pulled out flake, there's a hole. There's a pulled out flake over there, and there's a hole. So, but what's interesting is these holes are enormous. They're much bigger than the thickness of the flake. And what's happened in this case is you've got massive void growth around where the graphene was. The graphene is causing voiding to take place, and voiding in rubbers absorbs an enormous amount of energy. So we've got these large cavities that form. And what we've done is actually observe this directly in the synchrotron. We've done synchrotron X-ray computed nanotomography. I've got a video of this on YouTube, but what you can do, you can look at the tip of a crack, tip of a tear, and you can see these graphene flakes sitting in great big cavities, these enormous cavities here that form. And the energy required to form these cavities is enormous. So you're nucleating this cavitation in this particular case to get the toughening. But again, you don't have to have graphene to do that. Any 2D material probably could do that. But anyway, so final thing I want to talk about is commercialization. And we've had a rather interesting example of commercialization here by doing a collaborative project between the Graphene Institute, McLaren Formula One racing cars, and Richard Mill, who is the world's top watchmaker. They make watches and also sponsor McLaren. And we produced this watch with McLaren and Richard Mill, which is got graphene in and carbon fibers. And this watch is interesting. It has a graphene-enhanced rubber strap and a graphene-enhanced carbon fiber case. And it's only weighs 40 grams, or probably less than 40 grams. It's the world's lightest split-second chronograph for those who are experts on watches. And this was a very interesting project because it involved analyzing the composite case. This is the composite case of the watch. So this is a tomograph of the watch. It's around S because it's Swiss made. This company is a Swiss watchmaker. And this is a carbon fiber case of the watch, which we started with. We then impregnated it with graphene into the matrix of the resin. And you'll see here, this is again some CT scans showing the carbon fibers now with the graphene flakes around them. And this improved the properties of the watch and of the composite, but by a factor of say about 10 or 20% in stiffness and strength. So this led to an interesting product, and this is some of the stuff we did. We took this graphene flakes, we put them into the composite, and here's the carbon fibers. And you can see the graphene flakes are sitting between the carbon fibers here. We did Raman spectroscopy to distinguish between the carbon fibers and the graphene. This is the carbon fiber spectrum, very broad, graphene spectrum, very sharp. And we could see where the flakes were inside, reinforcing the composite. So we reinforced the carbon fiber reinforced composite with graphene, essentially. A very interesting exercise. And eventually, Richard Mill produced these watches. And if you want one, you can go to Pacific Place. Richard Mill have a boutique there. They don't have any in stock now, I'm afraid. They're all sold out. But it's an interesting place to. It's right at the top of Pacific Place among the high-level boutiques, and they sold the watch there, and it was quite an interesting product. Anyway, just to finish off now, hopefully, looking at the mechanical properties of graphene. We've confirmed the modulus of graphene is about 1,000 gigapascals. Strength, however, depends on the size of the flake, more like 10 megapascals, not 200 times stronger than steel. It's strong, but it's not very tough. Its fracture toughness is quite low. We can look at the mechanics of deformation quite nicely, explain everything using conventional shear lag theory. And it seems that the most important factor that controls the properties of these 2D materials is aspect ratio and orientation rather than the inherent mechanical properties. And a lot of people are trying to commercialize graphene. We did an upmarket commercialization, but there's many other ways of commercializing the material which are taking place in Manchester. Anyway, thank you for your attention.
I'm Feng Yan from Department of Applied Physics, acting as a moderator of this seminar. So, do we have any questions from our audience? Before you ask questions, please say your name. Thank you.
Yeah.
Zhao.
Okay, Xiaolin Zhao from Poly CE, Civil Engineering Department.
Yeah.
I have two questions. Thank you very much for your very nice presentation. The first question is about the fatigue performance of this graphene or graphene modified materials. The second question is related to, you mentioned the orientation of the graphene nanoplates. I was wondering, how do you control the orientation? Is there any mechanism, or is that easy to do?
Well, let me talk about orientation first. Orientation often comes with how the material's been processed. For example, injection molding will induce orientation. And we can use polarized Raman spectroscopy for measuring the orientation of the graphene. So that's quite useful. But there's only a factor of 2 difference between random orientation and aligned graphene. With fibers, there's a big effect of orientation. But orientation is not a major effect, but you can utilize it, and you can design injection molding processes that will give you preferred orientation, that sort of thing, to give you a bit of better properties. Fatigue, inherently, I don't think the material would suffer fatigue because there's no sort of mechanism. It either is elastic or fractures. There's nothing between, you know, it's elastic deformation, then breaks.
Right.
There's
But
no.
if we add it to other composites or other materials.
In a composite,
or
of course, it's the interface is probably failing, and what's happening is the interface would be failing, and that sort of thing in a composite. Yeah, but inherently, the material itself is, I would have thought, fatigue resistant. Yeah.
Okay. All right. Thank you. Yeah.
So any other questions?
Thanks very much, Professor Yang. This is Lei Yang from the Mechanical Engineering Department. And I'm very interested in you stress measurements using the Raman spectroscopy. So since my background is from impact dynamics, so I'm thinking, have you considered about using the Raman spectroscopy to measure the stress transfer when the strain rate is very high, which much higher compared with the choristic loading? And the second question is that have you envisioned that how can we integrate the Raman spectroscopy with the damage mechanics? For example, how can we use this method to improve the computational model accuracy to develop some high physical-based constitutive model and high fidelity-based constitutive model? That's all my question. Thank you.
Yeah. All our measurements have been done quasi-statically that I've shown. But we've always thought that we're using a laser. So it ought to be possible to have short laser pulses and to monitor high-speed processes. I mean, that's used in chemical analysis, I think. So it ought to be possible for mechanical testing as well. We've never done it, but there would be scope there, I think, to develop some way of doing fast Raman measurements in dynamic situations. I mean, there is one slight problem or potential problem with Raman spectroscopy, and that's radiation damage. That's damage from the laser. So again, if you use short pulses, high-powered pulses, that might help as well, so to avoid damage. We've always thought, again, the thought of using Raman in NDT as well. You can get handheld Raman systems, portable Raman systems now, and you can get fiber optic Raman probes and that sort of thing. So there's a lot of scope there in Raman spectroscopy. It's a strange technique. It's used in very niche areas. For example, De Beers Diamond Company has 30 Raman spectrometers for characterizing their diamonds. Drug companies use it for analysis of drugs and tablets and that sort of thing. So I think there's scope for somebody out there. It's too late in my career, but to take the technique and to really push it.
Okay, thank you.
Yeah.
So any other question?
Okay, hi, Professor Yang. Thank you so much for your presentation, which is quite impressive. I'm Zhao Hua from CE department as well. So actually, I got my PhD degree from the University of Manchester in
cool.
civil. Yeah, our group worked with the GAIC in our old North Campus, but not NGI. The GAIC, the Graphene Engineering Innovation Center.
Yeah.
Yeah, so thank you so much. I have a quick question about the graphene modified cement composites. So which is, do you think one of the missing link in the graphene mechanics at the moment is the lack of some kinds of quantitative framework connecting the graphene architecture, for example, the spatial orientation, the reaccumulation degree.
I can't
and
quite
the-
hear. I get a bit of noise on the microphone.
Okay. So, okay, do you think one of the missing link in the graphene mechanics at the moment is the lack of a quantitative framework or the quantitative architecture connecting the graphene, for example, the spatial distribution the reaccumulation degree or the connectivity in the matrix to the macroscopic properties of the composites? Thank you.
Yeah. So yeah, I mean, graphene does tend to agglomerate. You think of agglomerations and things like that, dispersions. Yeah, to be able to get to control dispersions is a challenge. Yeah, there's ways around that. For example, graphene oxide doesn't tend to do that as badly, but yeah, there's a lot of different data in the literature because people got different dispersions. Some people get really nice dispersions, some people get poor dispersions. Yeah, but yeah.
All right, okay. Thank you.
Professor Yang, thank
Yeah.
you very much for
Oh.
very stimulating talk and surprising to see the mechanical property doesn't link with Young's modulus of graphene. That really says this addition doesn't add too much. You can use other 2D materials. Okay, that implication.
Yeah.
My question is, in all these studies, probably there were no chemical bonds or bonds of strong enough between the 2D material and the matrix. Therefore, you have this large number of cavity formed. If somebody do a chemical modification of either of them, then create a linkage between them.
Yeah. Yeah, there's certainly scope to do that. Yeah. I mean, graphene oxide does tend to have better chemical bonds, and you do get rather superior properties sometimes for graphene oxide. But yeah, pure graphene itself is not very reactive, or doesn't stick to things very well. Doesn't even stick to itself very well.
Yeah. Yeah.
So
it's sliding. Yeah.
it slides over itself. Yeah. Yeah. And the interesting thing about the modulus, the important thing is that your filler modulus needs to be significantly higher than that in the matrix. But if it's 100 times higher or 1,000 times higher, it doesn't really make any difference. As long as it's higher, then it's the geometry of the material that's important, not
right. Yeah. That says that.
That really came out. Yeah. And so we've looked back at clay data from the 1990s, and it works. It's just as nice, just as good as the graphene. Yeah. It's the same as the graphene. Yeah.
Okay.
Same aspect ratio effects and everything. Yeah. Yeah. All the clay work. Yeah.
Yeah. May I just follow up that? I have one more question. If such a chemical bond can be formed between these two phases, then what kind of things we expect will be a little bit more like normal composites? Then, because if density,
you should get better stress transfer and more difficult pull out and that sort of thing. Debonding would be more difficult. Yeah, you should get tougher materials. Yeah.
Because the cavity is linked with a large amount of energy absorbed.
Yeah.
And therefore, there's a way people can engineer a material to have a different level of energy.
Yeah, but it's one of these funny things in composites. If you make your interface too strong, your properties may drop off.
Yeah.
Having a weak interface will
somewhere in the middle.
Yeah, somewhere in the middle will promote this voiding. This cavitation is enormously energy absorbing. Yeah. Order of magnitude higher than anything else. Yeah. This is again known from 1970s, people working on rubber. Yeah. Saw this cavitation. Yeah.
Yeah. Thank you.
Yeah.
Okay, any questions? Okay, actually, Professor Yang, I also have a question about your methodology of using this Raman spectrum measurement to characterize Young's modulus.
Yeah.
But at the first step, you characterize shift of the peak.
Yeah.
And find the relationship with Young's modulus. But that is based on the carbon material, right?
Yes, it's a unique characterization for carbon materials. Yeah.
Carbon material is a type of
graphitic carbon material. Yeah.
Graphite.
Yeah. For example, we've done years ago, we did a very similar correlation for polymer fibers. Like polyesters, Kevlar, aromatic polymer fibers, and you get a similar relationship. It's not the same relationship, but you get a.
But why this relationship is applicable for single layer graphene?
It's because, well, it's the shift against strain, but essentially, if you look at it, it's actually stress you're measuring. It's the stress on the graphene. The band shift depends on the stress on the graphene. So the higher the stress on the graphene, the bigger the shift you get. So it's a stress effect.
Okay. But the problem is for bilayer or third layer graphene.
Yeah.
It's not consistent.
No, because the layers don't all shift,
Yeah,
don't all strain the same amount.
Yeah.
They slide over each other. They stay behind. Yeah.
Okay.
The middle layer, 3-layer graphene.
Right.
The middle layer doesn't follow the 2 outer.
I see. So there's a shift between
The
layers.
2 outer layers stick better to the polymer than the graphene sticks to itself.
Okay.
Yeah.
Okay. So I think it's a very interesting fact.
Yeah, it is. But it's just when you get down to these atomic materials, there's funny things happening.
Okay. Another
But
question.
it's a technique. It still amazes me. This technique can look at atoms being deformed. Yeah.
Okay. Another question is about your X-ray nano topography that can show the graphene flex.
Yeah.
But why there are different colors for different flex? How can you identify the color?
I think it depends on the orientation of the flake. You're looking
Just indicate the
whether you're flat on or edge on or that sort of thing. Yeah. They tend to be mostly aligned because they get aligned at the tip of the of the crack or the tear. Yeah.
Okay. So different orientations, they show different colors.
Yeah. You may not see some orientations because you may not see them.
Okay.
It's tomography. It's the same as sort of medical tomography, but a nano version of it. Yeah.
Okay. So how about the resolution of this technique?
It's the theoretical, the quoted resolution is worse than what we seem to see. You shouldn't really see the graphene, but we do see it.
But it's related to wavelengths, right? If you have X-ray has a very short wavelength, you have a much better resolution.
It's a funny X-ray effect. Yeah. But you shouldn't really see features that small, but we do see them. We see, you think we see them.
Yeah.
But I think we see the edges of them. We don't see them flat on. Yeah.
Okay. I think it's a very, very useful technique.
Yeah.
Actually, I assume we don't have this instrument in our university.
Yeah, well, we have the very useful instruments. We have about 10 of them, and we also have a synchrotron, access on a synchrotron as well, which will allow you really high nano tomography. Yeah.
Okay.
In situ deformation, that sort of thing.
Okay. So we still have a few minutes, and actually I received questions from our online audience.
Yep.
So one question is about the integration of this graphene. How does the aspect ratio, dispersion uniformity, and alignment of this graphene nanofillers affect the percolation threshold for mechanical reinforcement?
Yeah, well, they all do affect, mechanical percolation. Of course, there's electrical percolation as well, which is something else we're interested in, but it's mechanical percolation.
Yeah, mechanical
percolation. Yeah. They all do affect it in some, all related to each other. We need to know all those properties, all the dispersion, the aspect ratio, and the orientation. They affect mechanical percolation, yeah.
Okay. So
exactly how? I mean, it's complicated. Yeah.
It's rather complicated. Yeah, I believe it's rather complicated. So what are the competing mechanisms between crack deflection, crack bridging, and the pour out of the graphene sheets in hardened ceramic or polymer nanocomposites?
Right. So this is now more like the rigid matrix materials, not the rubber. Yeah. Okay. Yes, you can get crack deflection and crack pinning, those sort of mechanisms as well, and pull out and debonding. And they sort of, they all make sense. You get sensible values for rigid materials like epoxy resins with crack deflection effects and pinning, pull out, debonding. It's the rubber where you get this excess voiding, where you get this very high toughening in the rubber, which is way tougher than the other materials.
Okay. So for this, for the practical applications of this graphene nanosheets, you introduced the use of the watch, right?
Yeah,
Just now.
we put them in the watch.
But
Yeah.
you also mentioned another company's car. It's a
The car as well. The company is McLaren Formula One.
yeah. Is it very useful for graphene to be included in some plastic
In
rubber?
the Formula One regulations, graphene is not allowed.
Okay.
So Richard Mill were the sponsor of McLaren,
Uh-huh.
and Richard Mill make the watch.
Okay.
And we worked with the McLaren engineers as well on
Okay,
on the
okay,
composite because they work on composites, but
Okay.
you can't actually use it in the car.
So graphene in principle can be included in this rubber.
You could use
For the
in
tire.
rubber components, so
Yeah.
the tires, or it could be important in the composite,
Yeah,
but it's not
yeah.
allowed. Formula One regulations are very strict on what materials can be used.
Okay. Okay.
To make it an even playing field. Yeah.
I see. Oh, okay.
Yeah.
But in principle, it can
In principle, it could be
improve
it
the
could improve.
lifetime of this.
Yeah, it could improve
tire.
the stiffness and strength. Yeah, of the car, the
Okay.
Formula One car.
Okay.
Yeah.
So, okay.
one, yeah.
Probably a last question. Okay.
Thank you for the talk from the Professor Yang. Yeah, actually, my major is in polymer science.
Oh.
Previously, I studied the PhD on the supervision under Professor Jinlian Hu in CTU. Yeah,
Yes,
I met
yes,
you
right.
before,
Yeah,
Professor
yeah.
Yang.
All right.
Actually, my main focus is on the nanofibers.
Yeah.
Now we meet a problem about is how to make a large-scale production of the nanofibers and how to enhance the mechanical property of the nanofibers. So we care about this question because those membranes, once it enhances the mechanical properties, it can enlarge its wide applications, such as for the bio-related or the sensors or others. But the basic problem is the productivity and the mechanical property. Then, what's your opinion about those questions? Thank you.
Using graphene in fibers, you mean?
Yeah.
Yeah. I don't think it's as suitable as nanotubes. I think it's if you're going to use what nanocarbon in nanofibers, I think nanotubes would be better.
Okay.
Yeah, because the strength of fibers tends to be controlled by defects.
Yeah.
And if you put large lumps of defects into fibers, then the strength will drop. Yeah. I mean, people have tried to put graphene into carbon fibers, and they've produced something which is a bad carbon fiber.
Yeah.
Because it just introduces defects into the carbon fiber structure.
Yeah.
So I think nanotubes would work better.
Yeah.
Yeah.
To use the composite consideration to construct the composite materials is a bad choice. But previously, we developed a technology to build the nanofibers to create the physical links to enhance the mechanical property of the fibers. But the problem is that how to prices to weighted the nanofibers is the problem, because once we weighted the nanofibers, it will infect the properties, porosities, and other things such as breathability or other things. Yeah.
Yeah.
Then how to develop the accurate technology to weight the nanofibers, I think it's critically important. But currently, I do not have the solutions.
Yeah, I mean, we've used Raman spectroscopy with nanofibers. It works really well. We've looked at electrospun fibers, electrospun fibers containing carbon nanotubes, and we can also cellulose-based polymers, other aramid-based fibers. It works really. Raman spectroscopy works really well with polymer fibers. That's where we came from originally before we worked on the graphene.
Yeah. Okay. Thank you.
Yeah.
Thank you, Professor.
Okay, I think time is up for the discussion session. So next, well, let's thank Professor Yang again.
Thank you very much for
Actually,
your attention,
long time.
everybody. Thank you.
Oh, thank you again, Professor Yang. To express our appreciation, we make this a special plaque for you with your name and the title of the presentation. Okay.
Thank you.
Yeah, let's. All right, and thank everyone for coming to this distinguished lecture. And now, this lecture is adjourned. Thank you.